Bonjour mesdames et messieurs, bienvenue à ce webinaire sur Predify, comment est-ce qu'on va améliorer la robustesse des modèles de vision et peut-être applicable à d'autres sujets. La présentation sera en anglais, donc je vais tout de suite basculer en anglais. So welcome everyone. We're really happy to have this webinar on improving our vision model robustness with Predify. Predify is a library that is provided inside ANITI, the Toulouse Artificial Intelligence Institute. It's going to be presented by Ruffin and Milad, who are going to present themselves in a couple of seconds. If you have any questions, please do not hesitate. There's going to be room for the questions, so you can use in your interface, you have a question chat, so please use it. The webinar is going to be recorded for your information, and you're going to have in the chat as well the link to the notebook that I sent to you previously, and it's going to help you for following the presentation. So once again, thank you for becoming. Thank you for being present. Thank you, Ruffin and Milad, and the floor is yours.
All right, thank you very much. So I will be the one speaking first. My name is Ruffin van Rulen. I'm research director at the CERCO in Toulouse, the Brain and Cognition Research Center. And I'm also a shareholder within ANITI, the Artificial and Natural Intelligence Toulouse Institute. So today we'll talk about Predify, this package. I hope that people can see the laser pointer. So while I'm speaking, do not hesitate to interrupt me, and do not hesitate to put questions in the chat if there's anything unclear. So yes, today we're going to talk about this package that we just put out. I want to encourage people, you can already start now, to go to this website and actually download the notebook. So this is what you should see when you go to the website, and you can download the notebook with the tutorial here just by clicking on this, so that in the second part, everybody can follow the tutorial together. The second part will be presented by Milad Mozaffari, who's one of the developers, together with Bhavin Choksi, one of the developers of Predify. And I will present a first part, but very quick, maybe 10-15 minutes, to give you some theoretical background about what we had in mind when we started to develop Predify. So let's start with this theoretical background. In this first part, I want to tell you how neuroscience can inspire new AI architectures. So the standard model in computer vision, you all know, is the feed-forward convolutional network. But we know that in the brain, there are many more feedback connections than the feed-forward ones. And so we were wondering, what are they for? Nobody really knows in neuroscience, but there's many ideas. And one idea is that these feedback connections could serve to do something like predictive coding. So I will tell you during my slides what is predictive coding, what is this theory. And so that's what we try to implement in our in deep neural networks. And in doing so, we were trying to make them more robust, and on the other hand, also more compatible with human vision. So the details that follow, they will be basically a quick summary of these three papers that we published recently. And this first one here was published in NeurIPS last year. So our models always include a feed-forward backbone. That's what you see with the green arrows here. This is a standard deep convolutional neural networks. It's trained in a supervised way, for example, for image classification. And so this would be the corresponding update equation. Typically, this would be a convolution followed by a nonlinearity like ReLU. But importantly, we also have in our models a feedback pathway, just like in the brain. And this is trained in an unsupervised way for a simple reconstruction objective. So the red arrow here represents generative predictions that each layer makes about the activity in the layer below. This prediction is called DN for a decoding layer, and we obtain this by simply deconvolution plus a nonlinearity. And this feedback prediction is actually incorporated into the representation on the next time step, which means that each layer is gradually moving towards the prediction from above. So that's the red arrows that you see here. We also have a balancing memory term so that the feed forward and the feedback changes don't happen too suddenly. This would correspond to the blue arrows here. And finally, we calculate the error, the epsilon, between the prediction and the representation, the actual activity, on every time step. And then we use this error signal, or in fact, we use the gradient of this error signal to update the representations on the next time step with the objective to minimize this error over time. And that's what the black arrow represents over here. So that's really all there is to predictive coding. But just in case anyone would still find that confusing to implement, we also introduced this PyTorch package called Predify, which anybody can download and use it to turn a standard network into a deep predictive coding network. And that will be the purpose of the second part of the presentation today. So in the experiments I'm going to show now, we have applied this predifying method to a few standard convnets, VGG16, EfficientNet B0, ResNet 18, and more. Now let's talk about performance. So typically what happens is that compared to the initial feed-forward pass through the system, which we always represent here at time step 0. So time step 0 is just when you go through the feed-forward system, no predictive coding. What do we gain by doing these predictive coding iterations? You actually don't gain much. You might even sometimes lose a little bit, as you see here, if the input is nice and clean. But really where predictive coding can help is when your input is corrupted. So here we have Gaussian corruptions by various amounts. And you see that the network iterations can really help improve the accuracy. So up to 6 percentage points as time goes on. And so indeed, if you look at the noisy input image here on the left, and you look at its reconstruction by the network after 10 time steps, you can really see that some denoising is taking place. But importantly, this is like an emergent property. This network is not trained for denoising, it's trained only with clean images, but it manages somehow to get rid of the noise using this predictive coding. And that's another advantage also of these predictive coding networks, is that because they have this generative pathway, you can always generate the image, an image corresponding to what the network is currently doing, and you can inspect it and understand what is happening. So we also verified that this robustness extends to a few standard types of adversarial attacks. So these are 3 different adversarial attacks: beam, RPGD, hop, skip, jumps. And you see that each time our predictive coding models are progressively, over time steps, less and less likely to fall for the attack. So on the y-axis, this is the attack success rate for different strengths of attack. These correspond to the different lines. So down is better on this plot. Okay, and the final thing I wanted to discuss is that we wondered also if these models maybe behave more like humans, then they might be susceptible to perceptual illusions, just like humans. So, for example, this type of pattern here, humans typically would see a white shape on top of black disk, but if you ask a current feed-forward vision models, it would just tell you that these are four Pac-Men. So what about our model? So what we did is we trained a simple 3-layer predictive coding model, just like before. This time we pre-trained the whole network, feed-forward and feedback pathway, with a pure reconstruction objective on the CFAR 100 natural image dataset. And then we added a classification head, and we fine-tuned the whole model on a very simple binary shape classification task. The model had to say whether it's looking at a square or whether it's looking at these 4 Pac-Men with random orientations. And of course, that's a very easy task. So just to make it non-trivial for the model, we added variable amount of Gaussian noise to the image. And so now that the network is fully trained, after training, the network knows about squares and it knows about these random Pac-Man configurations. Now we can also show two critical test conditions, two new configurations of the Pac-Man that the network had never seen before. Either they're looking all out or they're looking all in. And this one here, this is the illusory contour condition, because in this condition, humans would report perceiving a square, but not in the all out condition. So now what about the model? Well, here I show you the probability that the model will say that it's a square, probability of reporting a square as a function of time step for different levels of noise and for different patterns. And you see that specifically for the all-in condition in orange, for this configuration, this is 2 to 3 times more likely to be recognized as a square than the other test condition. So that's basically the Canisa illusion here. The final thing is that if you ask humans to judge the luminance of this square, they might tend to report that the center inside the square is slightly brighter than the background around the square here, even though they're objectively the same. And again, because we have a generative model, we can ask exactly the same thing from our network. We can simply look at the images that it reconstructed with the generative feedback. So here are 2 examples of reconstruction after 100 time steps. And you can see that compared to the original noisy image, there's less noise, obviously, because it's a denoising network. But there might also be a hint of a difference in luminance between the inside and the outside, between the shape and the background. And we quantify this simply by comparing the luminance for a few pixels inside versus outside of the shape. And again, so this is what's represented here for different levels of noise. And again, we found that this clear difference was visible only for the all-in condition in orange. So not only the network classifies the input as a square, so you can't read this, but just like humans, it also sees the illusory contour. It sees a difference in luminance between 2 locations that have objectively the same luminance. So to conclude, I showed you our proposed architecture inspired by the brain. I showed some properties of these networks. In particular, they tend to denoise the noisy inputs naturally. And as a result of this, they can show increased robustness to image corruptions and to adversarial attacks. And finally, we saw that these networks, but not the feed-forward ones, are susceptible to perceptual contour illusions in a way that's similar to humans. And so now is time to move to the second part and talk about our Predify package, a package that you can use to turn standard networks into predictive coding networks. If you haven't done so yet, I encourage you again to go to this link, or you've also received the link at the beginning, I believe. Download the notebook, and Milad will run you through the notebook and explain everything. If there's any question on this part, you could ask now. If the questions are more related to the code and how to use it, then you could keep the questions for Milad.
Up to now, no questions, so we can maybe move to the next point.
So Milad should be the presenter now.
Yes.
Do I have to stop sharing? I will.
But I don't have the option to share, I guess.
So right now, I stopped sharing my screen. Can somebody give the presenting right to Milad?
Yeah, I think the host needs to allow me.
Clémence, tu peux ouvrir pour Milad, s'il te plaît?
Okay, I think yes. Okay, so can you see the screen, I guess?
Yeah.
Okay, so we can start. I'm just changing to the Colab. Yes. Okay, hello everyone. I'm Milad Mozaffari, postdoc student working with Rufa at CERCO. And I'm happy to be able or to have this chance to present our Predify package in this technical focus. Okay, so as you may already receive, we are going to go through this notebook. And here for me is a bit different because I'm using a local runtime. But for you, if you click on the link, you should see something like similar to this one. If it loads, yes. And then you can run it using Google Runtime. It's all compatible. But if you want to save your changes, I highly suggest to use this button first. So you copy it to your Google Drive, and then you can modify any parts of the notebook and then save the changes for future reference. And also in your case, you are seeing some outputs. If you want to start from scratch, like the one that I'm going to show, you can use the edit menu and then clear all the outputs. Okay, so let's start. We are going to set up some packages. If you are going to use Google Runtime, then you don't need to install these packages. But if you are going to use your local machine, you have to install those. But we are assuming that all of you are using Google Colab. Then the only package that we need to install is Predify, and we can get it from the GitHub using pip install and git components. Takes a bit of time, and then it's done. Then we need to download some required files, which are mainly the pre-trained versions of the networks that we're going to use. So these cells are just some helper functions, which I didn't write them. I just took it from this Stack Overflow page. And then they allow you to download any publicly accessible file from your Google Drive or from any public Google Drive. And then you just need to run this cell to download all of these files to your local runtime folder. It may take a bit of time, but it should be fast. Then having these files ready, we have to set some global variables. By global variables, we mean a random seed to have equal results if you want, batch size of for the training setup, number of epochs, etc., etc. So these are not that much important for our purpose for now. Then the other important thing is the device that Google will assign. If you're lucky and you don't use Colab a lot, then it will give you a GPU. And in my case, because I'm using my local machine, then I have my own GPU, but you can check how lucky you are and which GPU you got. I hope you got the fastest one. Okay, the whole idea of Predify is to have your data set and you have your pre-trained network, as Rufan mentioned in his presentation. And then you give them to our Predify package, and it generates the Predified network for you. There are some default behaviors which we'll explain, but then you can apply further tuning on the generated Predified network. So we are going to do the same procedure here. So we start with the data set and with the pre-trained feed-forward network, and then we try to add the predictive coding loops and see how it improves the performance against input perturbations. So about the data set, we are going to use the SVHN, Street View House Numbers. If you click on the link, it redirects you to the dataset website, and these are all the numbers captured from Street House Numbers. And then the task is to recognize these numbers. Then in this cell, you just do some basic pre-processing that should be done on all kinds of deep learning tasks like normalization or center crop, etc., etc. So these are all the settings. Fortunately, Torch Vision has a built-in module for SVHN dataset, which you can use to load them. I suggest to run this cell because it may take a bit of time to download the datasets. And then here, for the sake of execution time, because we have time restrictions, we subsample the training and testing samples to 5,000 training samples and 500 testing samples. But if you want to use the whole dataset, you just comment these lines. And these two lines are to create data loaders. So when we have our data ready, it's time to talk about our feed-forward network. So we decided to use a standard feed-forward network that is well known to everybody. in the field, which is ResNet 18. We chose the smallest version of ResNet because, again, for the time constraints. And so just a quick preview of the structure. In ResNet 18, there are 18 trainable blocks or trainable modules, mostly convolutional layers and a classification head. And there are also some residual blocks where the input will be augmented to the output of that block. In PyTorch, these layers are further classified into 4 global layers, which we will use in the predification step. But here is the general idea of the structure of ResNet. But the standard ResNet is made for larger images size of ImageNet, which are 224 by 224. But here we are going to use 32 by 32 images, small images, and we have to adapt this structure a bit. So for this purpose, we have a function, which is ResNet 18 32 by 32, and in that we load the standard ResNet 18 and then change the first convolutional layer to have 3 by 3 kernel size, I think instead of 7 by 7. And we also remove the max pooling because we don't want to shrink the image size. And one way is to remove this layer and redefine the forward function, but the other way is to redefine the parameters in a way that it doesn't do anything. And that's what we do now. And of course, we have to change the final classification layer to have the target amount of output neurons or output components regarding the target tasks. Here we have 10 digits to be classified. So we are going to make the last layer with 10 components. And here I just create this network. I'm loading the pre-trained weights. We trained these on SVHN dataset before the meeting, and we have the weights ready for you. You already downloaded in the cells above. And this part just loads those weights. So we put our network in eval mode because we want to freeze all the batch norm layers or the statistics in the batch norm layers. We want to prevent any affection of input perturbations in our given network. Then next is to see, because this network is trained on clean images and it has a good amount of performance. So the next step is to see how much the Gaussian noise or any type of noise, here we selected Gaussian noise, can degrade its performance, its accuracy. So here I define some helper functions to do this accuracy test. It's straightforward. It needs a network, data loader, noise generator, and the device. It's just a straightforward loop of trying the network on the inputs. Then some functions to plot the images, and also some classes to generate Gaussian and speckle noise. So just run this cell to have these tools available. And then here before actually testing the accuracy, we want to see how this noise can affect the images. And as you can see, if it's the original image, then adding this amount of noise, I mean Gaussian noise with sigma or with a standard deviation of 0.5, 0.75, or 1, can degrade the image, the input image. And you can see in the worst case, everything is, I mean, all the information is lost almost. Okay, now it's time to see the performance. So we run this cell. It is using the function that we defined above. Under the Gaussian noise, I'm giving a particular noise generator to equalize the noise generation given the random seed that we defined above. And then we will wait to see the result. Feel free to ask me questions, especially during these running times. It can take a few seconds. Okay, so as you can see, here in the case of having no noisy input or having no noise on the input, which is the performance on clean images, we have, I think, performance above 98%. But as we add noise, like 0.5, 0.75, or 1 in the worst case, we have a significant drop in the accuracy, especially in the worst case, which the performance dropped by around 50%. So now the question is, can we solve this problem, or can we improve the performance by using our Predify package, or by adding predictive coding loops as Rupam presented? So we will see, and Rupam already showed some results, so you know the answer. But okay, so in a schematic view or a schematic form, we said that we have our existing network. So the idea is to add these loops on an existing network. So here again, we have our ResNet as the backbone, as the feed-forward backbone. And now we want to add these predictive coding loops, which we call them P-coder. So for example, here, we decided to have a single loop from the output of the first conv layer to predict the input image, and then from the output of the first layer in PyTorch implementation to predict the output of the P-coder below, and so on. But these backward connections needs another module to generate these predictions, which in this case we use conv transpose, and in situations that we have different layer sizes, like when we have, for example, strides of larger than 1 or max pooling, we have to compensate this size difference. For example, here in this part of the network, the layer size will shrink by the factor of 2. So we have to use an upsampling layer that by a factor of 2 to enlarge the layer, and then we use the conv transpose to predict. So one step is to make these architectures or make these modules, and the next step is to train them. So let's go for the first step, which is predifying the existing network. Here we import the Predify package, and we use the Predify function inside that. It only needs an instance of your network and then a configuration file, which includes all of the information about these P-coders. So let me show you the configuration file. The configuration file that we use here is the simplest one that you can use to predify your network. The first important field to present is the name, which will be used in the code that is generated. We will show later. For now, let's skip gradient scaling. I will talk about it later. Then this flag tells if you want to have the same shared hyperparameters for all of the P-coders. By hyperparameters, I mean, if you remember that predictive coding equation, there are some hyperparameters that controls the amount of influence of feed-forward drive, feedback drive, and also the error correction. So you can have, because each P-coder can have these hyperparameters, but you can have them shared across all the P-coders or separate hyperparameters for each P-coder. And you can define it, or you can change this behavior by this flag. You need to provide input size. We will tell you why later. But the most important part is to provide where you want to put these predictive coding loops. So here we can say in the simplest form, I just mentioned the name of the layers that I want to have the predictive loops. How can you know the name of the layers? When we created our ResNet, you can see PyTorch has some names for it, or whenever you make a network in PyTorch, you define some names for its internal module. And those are the things that we have to define in the config file. For example, I showed you in the image that I want to have a predictive loop at the output of this first convolution layer. So that's why I wrote conv1 here. But the next one was from the output of the next residual block, or the layer defined by PyTorch, which will be like this. So starting from the network itself will be layer 1, then it's a sequential because there are 2 residual blocks. Then we are interested in the second one. And then inside that, we are interested in the output of the convolution, of the second convolutional layer. So that's layer 1, index 1, and conv2. And that's what I wrote here. So you just write a cascade of these layers, and then Predify does the rest for you. We will come back to these config files later, but that was only a sample, smallest sample of the config file that you can run to have your predified network. Okay, now After running this function, it will generate your predefined network as a code file. There are some reasons to generate the code instead of a new module, which I'll explain later again. But as you can see, when you run this function, it also generates some warnings, allowing you to know what are the modules that, or what are the components that are assigned by the default value and are missing in the config file. So you are aware of that. And then when we have the code file, I will show you the code file as well. You can just import that, import the built module, and then create an instance of that module. So for creating a predictive coding version of your network, you need to create an instance, providing an instance of the feedforward backbone and the flag about building a computational graph or not. Here, because we want to show a demonstration of how to train the feedback loops or the feedback weights, we set the build graph flag to true, but later, in order to test our network, we can turn it off. So just run this cell, and you can see again, you have the representation of the backbone, the same as the present 18 that we saw before. But in the very end, you can also see the configuration of the P-coders, as showed in the figure above. Okay, now that we have an instance of our predictive coding network, the next step was to train it. So here the idea was to use clean images for the given data set during the training of the feedbacks. And the feedback weights should be trained in an unsupervised way using reconstruction objective. So for this purpose, we just need to define an MSE loss and compute this loss at those locations where each P-coder is predicting the output of the P-coder below, and we have the representation of the P-coder below, and we compute the loss between them. Then we do it for any P-coder that we have. We compute the summation, and we apply the optimization on this global loss value that we have. But the other interesting thing is that we do it only for one time step, which means for all of the predictions, we only use the representation of the feedforward backbone without interfering any of those terms in the predictive coding equation. This is the simplified dynamics of the predefined network. So at each time step, each P-coder updates its output. But if it's the first time step, the output will be simply the feedforward representation. And then for the further time steps, it uses the predictive coding equation that you saw. But then after computing the output, it computes the prediction, which is the prediction of the layer below, and computing the prediction errors to revise its representation for the future time step. So here in this cell, we are just configuring the optimizer, the learning rates. I'm using different learning rates for different P-coders because of the different range of gradient values, but in my experience, it doesn't matter. And then if you want to track the changes of the loss function, you can load the tensor board. If you're using Google runtime, then you should be able to see the tensor board panel here. But in the local runtime, I cannot. So I have it open in another tab. We can refer to it later. And now it's time to run the training and testing loop. These two functions, to train P-coder and eval P-coders, is included in the Predify package, so you don't need to be worried about. All you need to do is to give your Predify network instance, your optimizer, your target loss function, and then your data. These are the important components. And then the Predify package does the rest for you. So for now, let's run it for a series of epochs, depending on the GPU you have access to. I have a question. I think my runtime is, oh, no, it's fine. I thought for a minute that my runtime is CPU. Okay. So in the meanwhile that this part is running, I would like to show the internals of Predify package for those who are interested. Might be a bit technical, but I think it's worth mentioning how Predify works. It will be quick and brief. I don't want to explain everything. So I would like to start with with predify.modules, which includes the smallest module in predification process, which is a pcoder. So most of the time you will use pcoder n. I will show you how. And it's the smallest module that manages all the updates about a predictive coding rule. So inside it, there will be the forward function, which you can see those dynamics that I explained earlier. If it's, for example, the first time step, it only uses the feed-forward representation. I know it can be a bit complicated here, but trust me. And then if it's not the first time step, then it uses the predictive coding dynamics. And of course, using those hyperparameters, which is the feed-forward, feedback, and also the error. The other components that you may use it during your experiments are these, let's call them memory tensors. One of them is the PRD, which includes the prediction of each pcoder at each time step. The other one is GRD, which includes the error gradients that will be used to correct the representations. And the other one is REP, which stores representations of the pcoder. So it acts as a memory of that pcoder. I will show how to use them later for our experiments, but just keep in mind that these are inside our pcoder. Then we have the network module, which are actually the basis for creating a predictive coding network. These are providing all the required basic functions that your predified network might require, but then you can manipulate them in your final version of the network and add more functionalities if you want. Here we have two versions. We have PNet with same hyperparameters or PNet with separate hyperparameters. Here we are going to use separate hyperparameter versions, which is a more general version. And then here you can see there are all the required hyperparameters for all the pcoders. There are functions for managing the flow of the information inside all of the network, through all the network. And for example, one important thing is to know which time step the network is working on. And for this reason, here is like this. If we provide a new input to this function, by this function, I mean the forward function of your predified network, then it will be considered as the new input at time step 0. So as you can see, the network will be reset. All of its internal components will be back to time step 0, and then it starts new from scratch for a new series of time steps. But if you want to continue working on the previously assigned input, then you just don't give it any new input. You can assign none as the input. And then it continues applying the same given input, I mean the previously given input, which is recorded at input memory, to the backbone and run the scenario. And other functions, I mean general functions like get hyperparameters or setting hyperparameters, updating, anything that will be generally needed for a predified network. So, and as you can see, they are inherited from nn.module, which means they are fully PyTorch compatible. And finally, in the utils, there are some utils for training, as I showed you in the notebook. So I don't want to open them here now. And let's see what's the generated code looks like. Okay, when you call your predify function, and you give it a network, then a similar code like this will be generated for you, in which you can see it will be inherited from those basic networks that I showed you earlier. And then without any redundant thing, it only creates those predictive modules for you. And the rest will be done by the basic network itself, by the forward function that is defined there. And these are all the things that is generated by the predify function there. Like what's the P module? here the P module is the module for predictions, those conf transpose and upsampling, for example. And then what's the P coder? Here it's P coder N, and then the P module for this P coder. And now the magic is here. How can we run these P coders without changing the structure of the feed-forward network? And the trick is to use forward hooks in PyTorch. So forward hooks are like event functions that will be attached to any module, any PyTorch compatible module. And then they were called as soon as the forward function of that module is called. So here, that's all we need. At those locations that we want to have our P coder, we attach this function. And what's the function? For example, for the first P coder, the function is to call the first P coder with appropriate input and hyperparameters, for example. So it means as soon as that particular module in the feed-forward backbone computed its forward representation, then this function, which means this P coder, will be run, and then all the internal equations and dynamics will be updated. And in the end, the output of that P coder will be returned, which can be used for later process. So that's the whole thing that happens here. And the reason, and one reason that we selected to do code generation instead of other methods is that it gives you more flexibility to edit this code in a way that you want, or you can keep it as it is. And the other reason is some kind of ninja optimization in the execution time. And if I want to show you, because so far we talked about the default behavior of Predify, if I want to show you more sophisticated examples of the config file, I can show you the one we use for PBGG in our works. So here, these are the same as before, but you can see for each P coder, we could define our own predictor module instead of letting Predify choosing upsampling and conf transpose. And also we assigned some target hyperparameter values to each of those hyperparameters for each P coder. So you have all the flexibility to define everything that you want here. Okay, let's go back to the notebook and see how it goes. So again, depending on your speed, you may be in a different epoch. So let's stop it. You don't want to go until the very end. And you can go up to the TensorBoard view. I can go to the next tab, which I have my TensorBoard. Then you reload your TensorBoard. And I usually turn off the smoothing. So you can see across the training epochs, only the feedback weights with MSE loss. We have both convergence on the training samples and the testing samples. And also I tried to track a sample image reconstruction from the very first epoch. Here, I think it's epoch number 2. Oops, it reloads, sorry. So on the left, you have the original input, and on the right, you have the reconstructions over epochs. And you can see as I go towards the final epoch that we had so far, we have better reconstruction. So it means the training is working, and we have very good reconstruction. Okay, let's go back to the notebook. And here, we stop the training because we don't have time to finish the training. So instead, we want to load a pre-trained PresNet. So again, we trained a predictive ResNet exactly with the same architecture that I showed here with the whole SPHN dataset, and you can load the weights. Again, you download them earlier in the download stage. And here you can see I set the build graph flag to false because I want to test against some noisy inputs. And also we put it again in the eval mode because we don't want the network, or it's better to say we don't want the batch from layers to get adapted to the noisy situations. We want the pure influence of our predictive loops or Predify package. And you can see these are the default parameters assigned by the default behavior of the Predify function. So let's keep them for now and see what happens. Okay, the first thing is to see if our network, if the Predify network can remove the noise from input images. Here we are going to use the Gaussian noise, and what we do is we go through different number of time steps. Here we go through 10 time steps, and we give the noisy input. Here we apply the Gaussian noise on the input, and we use the Predify network on this input. So here you can see in the first time step, I gave the network the input, and then for the further time steps, I just gave it none. So how can we check the reconstructions? As I mentioned earlier, inside each P-coder, there is the PRD tensor, which stores the reconstructions, which stores the prediction. And as we know, the first P-coder is predicting the input, so it's the place that we can find the reconstructions of the input. So when the execution of this cell is done, we can go to this cell, which is just a visualization code. And that's all we can see. So here is the original image, some sample original image from the testing set. These are the reconstruction of the original image, which means if we show these images without any noise, after 10 time steps, how they look like, how the reconstructions look like, they are pretty the same. But the interesting part is when we add noise to the input, and then what happens in the reconstructions after 10 time steps. As you can see, even in some cases that most of the information is gone, some parts of the digit is back, is reconstructed or is restored, which should help to regain the accuracy, and we are going to evaluate it as well. So here, again, I have some helper functions that allows us to evaluate a predictive network, because for a predictive network, we have to run it on several time steps. So it allows us to evaluate our predictive network over a particular data loader with a particular noise generator and over some time steps. It's pretty the same as the previous function, but here we run the network for multiple time steps. And let's just run this cell. And now we test our predictive ResNet on Gaussian noise and speckle noise. I run both of the cells at the same time because when we are talking about the results of this one, this can be done. Again, if you have any questions, you can ask me now. It takes a bit of time to be done.
Thank you, Milad. If there is any question, it's time. Huh? You can do that. Maybe, Refin, do you have a conclusion or kind of wrap up?
Sorry, François-Marie, it's actually not finished. It's just we're waiting for the cell to complete, but there's a little more things to say.
Okay.
Okay, so this cell is done, and the idea was to compare how the performance can improve by predication, or our Predify package, or the predictive coding loops in comparison to the feed-forward baseline. So here in this plot, in the left plot, you can see we have the same curve as before, the performance on different amount of noise levels of the feed-forward backbone for Gaussian noise. And then we tested the Predify network, the Predified network, for 10 time steps. And here is the performance after 10 time steps. So we can see at all of the noise levels, we have a significant performance gain. And also in the right plot, we showed this performance improvement or accuracy improvement for each type of noise. And as you can see, for clean images, after 10 time steps, we have a small amount of drop, which is not significant at all. But for other amount of noise levels, like 0.5, 0.75, or 1, we can have around, let's say in the worst case, we can have, I mean by worst, the worst amount of noise, we can have around 13% of performance gain. It can be the same for the speckle noise. So again, This is the feed-forward performance on speckle noise, and this is the predefined version after 10 time steps. So at all levels of noise, we have performance improvement, and here we have the improvement in accuracy over time steps as before. So that was all about the main part of the presentation. I know there are some questions like about, for example, the arbitrary choose of hyperparameters or choose the number of P coders. I've already prepared some cells or some code to explain some of those. I don't want to run them, and just maybe because we don't have enough time. Just to show you some results, you can already. I have added some text, so you can also study yourself. But here I just try to show the impact of adding each P coder. For example, here in this loop, I'm adding P coders one by one by just changing the hyperparameters. You can investigate yourself how. But you can see with only one P coder, the very first P coder, we don't have any performance improvement. By the second one, we have a bit of improvement. The third one, we have a very good improvement, but only for the worst noise level, not for the others. And as we add more P coders, we can have better performance improvements. Maybe a bit of compensation for the worst noise level, but not the others. And about how many time steps, it's again something empirical. So we also tried with 30 time steps, the same task. You can see after around 10 time steps, it reached it's saturated, so no more improvement. But on the other hand, more time steps degrades the performance on clean images more. So you have to find this trade-off when you want to stop. About hyperparameters, I think I don't have enough time to discuss. I just want to tell you, okay, there are some options like grid search or even supervised training of hyperparameters, but of course we don't have access to noise, or we don't want to give noisy data to the network during training. We don't want this information leak. So what can we do? We can choose one particular noise like Gaussian noise, train hyperparameters on that, or tune hyperparameters using that, and then test against other noise. We showed this in our research work that it can work, but of course, it won't be optimal for all types of noises, which if you are interested, you can open the links I provided here to a more in-depth exploration about hyperparameters. And I think the last one I will skip for now. So we have time for questions. I will stop my. Yes.
Well, you might need your notebook for answering the questions, if there are any. People, don't hesitate to ask questions. If you've been following along the notebook, it's already very good. If there is any question about the notebook, I think people should be encouraged either to ask now, don't feel shy, or you can always contact us, Milad or me, later and ask your questions. If there are no questions now, I'll just say a few words of conclusion. I think the general idea for today was to give you this notebook. It will remain on the web, of course, so even if you didn't download it today, you can always download it later. And the notebook is just one example of a simple, typical use case of how people might use Predify. Of course, your network is probably not ResNet 18, your data set is probably not SVHN, but the idea is that if you have a similar problem, you have a feed-forward network, you have a data set, and you have problems of robustness, you can just take this notebook and basically replace the data set, replace the network, and it should be easy for you then, based on this notebook, to figure out exactly what you have to do in order to predify your network and to test it and to adapt it to your problem. And what Milad was discussing at the end, and we didn't have time to go into the details, but it's all in the notebook, is that, of course, the default situation, it may not work for everyone. If you end up with your network and your data set and the default Predify hyperparameters do not work for you, that's not the end of the day. There's other things that you can do, and it's all explained in the notebook. There is alternative solutions. They might require a bit more coding, but it's possible. And of course, if nothing works, then you can always ask us. But it's possible that there are some problems for which Predify doesn't help, of course. It's not magic, even though it looks like a magic wand. It's not really magic, it's just code.
Yeah, I think it's interesting to let us know which problems Predify cannot work. Can be also a good question.
Definitely.
Okay, well, very thank you, Milad and Ruffin. And please, I just would like to apologize because I make an interruption during your presentation because I was a little bit busy with some technical problem that we have. So if some of you met some difficulties to connect, please receive our apologies. We're going to fix the topics. That's direct live, it happens. Once again, thank you very much, Ruffin and Milad. I just recall that these are, you know, scientific results of ANITI, so it's for your usage. One way also to thank Ruffin and Milad is, as you understood, is also to come back to them when you use it, when you evaluate them, if you encounter some difficulties, and also if you encounter some joys, you know, they would be really happy, and it's a way to thank them for the presentation and the very good work that has been done. This work is going to be available afterwards through the slides and the replay, so you're going to have the link, and for sure, as Ruffin said, also the link to the notebook. I also would like to make a prayer to all of you. If you have some feedbacks in these focus techniques, I would really be happy to have them. That's something that we think important in order to make, you know, AI available, and you know, the high level AI available in our ecosystem. So any feedback from your side would be really appreciated in order to make us progress on this type of presentations. And by the way, we discussed about robustness. We are going to continue with robustness, and the next technical focus is going also to be on that topic. So I propose you the next one on the 18th of February regarding other ways to address robustness with the lip-sync functions. So thanks for attending. Thanks, Ruffin and Milad. We're going to close, and see you next time. Bye-bye.
Bye.
Thank you.